In the second lab, we're doing the same experiment as in the previous lab. And here we assume that the charge is distributed evenly across the tape and determine the excess charge on the tape. The result that I got this time is Q equals to 3.138 times 10 to the negative 8 coulombs. The physical principles that I use in this lab are Coulomb's law, Newton's second law, and the superposition of electric fields. Here we divide the tape into infinitesimally small portions and consider each portion has a charge dq. According to Coulomb's law, the electric field on each particle on the U-tape equals to 1/4πε0 times dq over r squared, and the electric force on each of the particle is dE times q. And here q equals to dq. And then according to Newton's second law, the net force on the U-tape is 0 since the U-tape is motionless. And from here we can get that the gravitational force is equal to the electric force on the U-tape. In this lab, we make the same assumptions as in the previous lab, that the air resistance on the U-tape can be ignored. And we also assume that the U-tape that I've made have about the same amount of charge evenly distributed along the length of the tape. What is different from the previous lab is that here we assume that the U-tape is a line of charges instead of just a point charge. Based on the assumptions, I got the computational model as shown in the picture. I treat the U-tape as a line of point charges and the bottom tape as a part of the surroundings. Then I superpose the electric field on each point charge and get the net electric force on the U-tape. Here the electric field on each point charge is shown by the green arrows, and the electric force is shown by the white arrow. Finally, I get the estimated value of the charge on the U-tape by plugging in different estimated values until the magnitude of the electric force and the gravitational force on the tape are the same. I'll explain more about the process later. I did the same experiment as in the previous lab this time, and I got a different distance between the tapes, which is 0.035 meters this time, and all the other measurements are the same as in the previous lab. I also copied the function code in lab 0, which is shown in this picture, and it just represents the Coulomb's law. This part of the code helped me to create a line of n uniform point charges with a given total charge. Here I assume that there are approximately 10 point charges on the U-tape. The most important part in this code is the loop as shown in this slide. Each iteration of the loop is calculating the electric force on one individual portion of the tape so that we can find the total electric force on the tape once the loop is completed. After I plug in several different estimated values of the BQ and run the code for several times, I finally get the same magnitude of the electric force and the gravitational force as shown in this slide. The calculations done by the code helps me find a value of the charge on the U-tape that is close enough to the real value. Here are two more questions for me to answer here. The first one is a comparison between the two estimated values that I got in this lab and the previous lab. The estimated value that I got in the previous lab was 2.33 times 10 to the negative 9th coulombs, and I'm sorry that I forgot to write the unit here. And the value that I got this time was 3.138 times 10 to the negative 8th coulombs. I found that the second value is approximately 13 times as big as the first value. The second question is, why do these estimates differ, and which value is more likely to be closer to the real value, and why? I think the assumptions made in lab 2 is more close to the real reactions between the two charged tapes, while the assumptions in lab 1 is more generalized. In this case, I think the estimation in this lab is more accurate. My closed group link is here for reference and for conclusion. When I used the value that I got in the previous lab as the estimated Q value, the code returned an electric force that was smaller than the gravitational force on the tape. Since the electric force must equal the gravitational force, I changed the Q value to a bigger one and made the two forces equal to each other. The result is reasonable because the charges on the U-tape not only bear a force on the y-axis, and the force on the x-axis will decrease the force on the y-axis. So the overall charge should be larger in order to ensure force equivalence. And that's it. Thank you for listening to my lab report.